So now we start lecture proper. So repeated what we did yesterday. We basically just put all the bits and pieces into place so you understand where things come from, but you also understand the subtlety that arise when you put these things together. So it's non-trivial. And I talked yesterday about the fact that I do not treat the matter sector with Dirac, and I want to explain also this briefly, because if you do Dirac's theory, that we followed for the photon, right? We followed it exactly step by step what you would do for the Dirac particles, so positrons and electrons. You would also end up with a quantum field theory. So that means you would have also annihilation and creation operators for fermions. The problem with these beasts, as also Markus might talk a little bit about this, is that they are not operators. This is a misnomer that really leads to a lot of confusion. They are actually distribution valued operators. And as you might have learned in analysis, distributions cannot be multiplied. And that's the origin of all the problems of regularization and renormalization. Now, if you, however, go into the non-relativistic limit and you only have one quantum field left, this is the photonic one, it's still interacting, right? But with a first quantized theory, it's still complicated, but you get rid of most of the cutoffs or most of the regularization problems except of one. And this you will see today. So by going to the non-relativistic limit, you avoid a lot of troubles because they are unsolved in a non-perturbative theory. Again, in a perturbative theory, again, Feynman, Tomonaga, and Schwinger got the Nobel Prize for the reason to show that whatever you do in the perturbative setting, however you regularize, that means modification, Markus will talk about this, it will always give you the same answer. In a non-perturbative theory, that's not the case. And that's why we do not know how to handle interacting quantum field theories. So non-relativistic particles it is. And if we assemble all the bits and pieces that I gave you yesterday, it's actually quite boring. It looks like this. Or maybe you find it not so boring, but it just looks like a normal Schrödinger equation with a few add-ons. But this really, the full theory, you can just deduce from special relativistic energy dispersion relations. So let us go through them step by step. So up here you have what you in the textbooks usually read as minimal coupling. Now you know this is fixing the phase. And you fix the phase in such a way that you have the Coulomb gauge. So these fields, these quantized fields that I also introduced yesterday, they are the Coulomb gauge vector potentials. We have a magnetic field here. So this is the Stern-Gerlach term. That's why it's called Pauli or not Schrödinger, because on the same order of 1 over mc squared, you also get the Stern-Gerlach term that's basically doing the following. If I have spin down, it goes this way. If in a constant magnetic field, if I spin up, it goes that way. That just comes out from these expansions. Then we do Coulomb gauge. As you have seen, the Coulomb interaction comes from the quantization of the electromagnetic field together with the quantization of the matter system. So this is actually a photonic energy expressed in terms of electronic properties. And again, this is a choice. We choose to express certain parts of the coupled system as what we would then assign to as matter and other things that we would assign to as photons. And you will see today that even this distinction is not exact because you cannot distinguish light and matter, at least with our current theories. So this is the electronic sector. Now, QED would be a theory of electrons and positrons. So this would be a little bit boring. You couldn't do any condensed matter or quantum chemistry. So as an add-on to QED, we add also the effective nuclei. Nuclei are made out of protons and neutrons and stuff. So you would need to do things like QCD to describe them. So I would have to add further layers there that, of course, are a little bit, even for me, an overkill. So what you do is you say, yeah, each nucleus has an effective charge and effective mass. and an effective spin, composite particles. And it looks, of course, the very same. You also do Coulomb gauge because they couple with charges. And then you have the interaction between the nuclei and the electrons, and then the free photon field. And that's the Pauli-Fierz Hamiltonian, and that's the starting point of everything we do. There are some subtleties, mathematical subtleties that Markus will tell you about, but that's currently, I would say, the only rigorous light matter coupling theory out there. All right, so, and what we want to do today is to list basic characteristics, at least in my part, and Markus will then subsume everything in his second part when he talks about the math a little bit. List all the basic characteristics of the Pauli-Fierz Hamiltonian in different gauges. So there are a lot of different characteristics. Again, lecture notes you will get. There is a lot of further information there. I only look at a few. And in order to understand what is happening to this Hamiltonian, we actually consider the exercise number 4. This is again the same exercise that you did yesterday, but the difference is you will have very many modes, right? Because if you look back here, there is an integral here. Where is it? Oh, no. Where is the integral? There's an integral. If you discretize it, you have a sum here, right? Because of course on a computer, we cannot represent an integral, so we discretize it. But essentially, you will have very, 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 very many modes. So what do they do to your quantum particle? We ignore, so there are no nuclei in our case, there's just one electron. And that means all the other terms fall away. We ignore, we do the dipole approximation, so this term we just cut off. So it's essentially, and I will explain the dipole approximation again, essentially a simplification of this Pauli-Fierz Hamiltonian. And let us please take a look at notebook 4 and talk about it, what you find, or try to do it together, really. I think it's important.
This. Wrap the thing around.
Log it off, I guess. Nice.
What letter is it? I have a shape for this.
Danke dir für deine Hilfe. Ein wahrer Held der Arbeit. Das hat nur 10 Stunden.
The notebook on GitHub.
Is the notebook not on GitHub? Is the notebook on GitHub?
Only 3 notebooks. You only uploaded up to 3, and I thought you were uploading the.
Oh, this was my mistake. Yeah, no, I put it online immediately. Then it's hard to work on it. Can you do it fast? Thank you. You're much faster than me. I'm pretty sure.
Not sure about that.
Can you send me again the notebook for executed? So very well prepared, obviously. So let me see, but I can show it to you here in the meanwhile. Questions? Notebook 4. I apologize. This was my mistake. So here it is. So it's the same Hamiltonian as yesterday, except now there is a sum going up. This one looks dandy.
In the terminal.
Sum. So it's the same Hamiltonian as you did for one mode and one particle, still one particle. And then you can go through the steps. And you know already here, this is the trick, you just rewrite this, this stays the same, it's just the one particle renormalization of the frequency. And then you can try to solve with 4, many modes. But is it online now?
1 second.
1. Well, it sometimes shows it in here. Now here.
You don't have to put the URL. You can just do it.
No, other stuff. Yeah, definitely.
Okay. Should be there, Ruby.
Perfect. It should be there. Thank you so much. Sorry, my mistake.
The exact same thing.
That's this problem. Like yesterday, I was looking at this.
Yeah,
And I thought there was a bunch of typos. Yes, exactly. So you should open the Jupyter notebook. Right. On the Jupyter lab. There it renders.
Then
No, I prepared the instructions for coaches.
Maybe I should get into this.
Future.
So is this diagonalize in terms of E, or is this the file? Just they say how you find you display. Yeah, sure. We will now use 5 and 6. Yes. Or should have done it. Yeah.
Yeah, but as far as I know, we just do
Yeah.
7 because it's more than enough.
Okay. want it? And I think there's 7 people.
We could.
Yeah.
Yes.
Yeah.
So that would be a 2 button. And I think that
You make clearance.
yeah, I think that also
It's already split, but I think. Okay. That's good.
Yeah.
Got it.
One more.
Yeah, Leo.
Yeah.
Should we find E2 or should we assume we have E?
Assume you have.
Oh, yeah.
Like E is
The operator.
Yeah.
That's what like a diamagnetic. No.
Okay, so if you only want to. So that's, okay, then I'll. Okay, then I'll.
Tomorrow
No, 8. It's 7 is.
Okay,
Okay, cool. We'll do those. Yes.
All the answers from
Yeah, that one, I think we didn't. Those are just.
yeah, exactly. So just,
For the lots, but for the record.
yeah, there are other ones.
Somewhere for you, like.
It's because it's something different.
Try to fix it last year. Even just say, yeah, it's very annoying. Some, I mean, some fine, some. Like what?
Oh, yeah, yes.
I think so.
It was just this,
Yeah. Like some square root.
So I think, yeah, it's pretty much.
also that in the last thing, there were plenty of time. Exactly, that's what I was.
Speech voices. They can ask you whether the lecture.
I mean,
does your computer heat up hot enough? Just like, I don't know. What took.
do you have any solution to give?
Sometimes I do have like hand warmers in my bag during the fall and winter. I don't think I have.
That's okay, I would survive. Oh, yeah. What?
There's nothing there.
Let's see, look. Massive dodo.
Dollar notation, maybe it's not the right one for GitHub.
Did you just change it? Or?
It's always like that. Oh, when it's over here.
I only checked this.
No. Is it?
I like it.
Then you can. Yeah.
Look.
Yes. Later today. But on this Jupiter doesn't work.
No, on the Git here, like this.
No, on the Git it doesn't work.
But this one works. Not all of it. Okay.
No, that's random.
Okay, okay, then
depends on the browser.
Never mind.
That's really the browser.
Yeah, okay. And never mind.
Yeah. We never figured out how to make it work.
Yeah, okay, sure.
It's like it depends on the browser as well. Then,
Yeah.
Like gamma equals 1.
Okay then.
what do you have? But you can check with it.
I'm thinking this through.
Did you guys upload the? Did you guys get the notes?
Yes.
It's gone from 28 sides all that. If
Oh, that one. Might have to use this.
How is it going? Good. Finished? Not yet? Okay. I mean, this is really the important one of this first part of the morning. So we can skip the second one, which is a redo of that one as well in a different case. So take your time. Go as fast as you can. Talk to each other. You can be faster that way.
In the
We're looking at.
repository, it was on notebook 3.
Oh, no. Sorry, I missed that part.
By defining omega d.
1.2 or whatever it was yesterday.
Yes, partially diagonalized.
So ja, ich werde wahrscheinlich die Zeit machen.
Ja.
Soft.
I know I'm happy to propose for the future. We didn't give it. No, it's like.
Also, it's a minus IH bar del, and the eigenstates are plane waves, right? E to the IKR. So
Right now I can
apply the
we will leave
and you get IK to the IKR, and then minus I times IK is
Oh, good. This way.
Was een probleem met het
Mine.
Wir haben exakt das Problem, wir machen genau das Gleiche. Und dann kriegst du das Plus von den Photonen. Wenn du unser Paper aufmachst.
Aber schau, weil er hat dann, was er dann im nächsten Schritt macht, ist, er schaut sich Hardware an. Jetzt lustigerweise, er macht Hardware bei Borden. Das ist ja wirklich nur die Hardware-Prozess.
I check.
well, the minus is
Addressing it in the original basis.
minus sign comes in when you like renormalize the E and you just like add that constant. Wenn du irgendwas Spezielles brauchst, right? Leave the square or whatever. You get the minus terms, which is like this
Iterated
renormalization of
Ja, der hat die Wärme. Wärme halt.
Genau, eben die Photonenthermie. Ja. Ja, genau. Das ist ja, also wenn du wirklich 1:1 dieses Minus muss zu einem Plus werden. Das passiert genauso wie eigentlich steht da ein Minus originalerweise. Meine schnelle Herleitung steht ein Minus 1. Und dann steht der Plus hoch I. Und dann kriegst du zusammen.
I think that like basically like these first two terms are like from expanding square plus A. You expand that square is the first two terms of the H bar squared constant. I think
Art wurde es gemacht, aber weil es ein Standard ist.
Genau, da hat es gemacht, aber er leitet es ja eigentlich her. Der Pauli-Fierz.
Oscillator.
Pauli-Fierz Hamiltonian hat.
Genau, der ist ja gegeben, deswegen schau dir mal nicht an, wo er den herkriegt. Und jetzt, wenn du das nicht machst, dann siehst du es ja nicht.
Yeah, I think so.
Oh, okay.
All the photons are not interacting with
Right.
each other, so just talk to them one by one.
I guess it's
Yeah. Okay, yeah. Yeah, so everything will then.
But I pointed the paper.
That's really,
It depends on the
I need like symmetries.
also this is it right there. So I assume that it so retail is subsets of but it's starting from
But so I tried. It's not the budget. And now.
than I expected.
For you.
Yeah, and I also don't read.
This is
My
basically
project that I'm on is supposed to be QD, but I'm doing conical intersection. So like when electron state crosses, and it doesn't really but it is, and I have to do something because of the project money. I have to do some QD at some point.
like most of
So, the sun, is it over? What word is it? Only the last one.
assumption that the
I
diamond
think it should be.
I see, is it what, isn't it? Like,
artifact.
but no, it dies around, because they'll make it.
I guess like they took care of diagonalizing. Yeah. I mean, I asked Leo earlier, and he said that we should diagonalize in terms of
I see
that basically like finding D would be the like many photon equivalent of an exercise like 1.1, and so I think that
Okay, you collect.
I think that they just aren't having us do that yet. It's probably more complicated and like many oscillators.
I see. Okay. Okay, and then you can use the you just change.
Of course.
Obviously.
Will that be kept wide? Well, it depends on whether if you can do the dipole approximation for the whole chemical, then you can exactly, but that will not be generally true. I don't know, at least that's, but again, it is on this dilute argument, right? So there might and what we need to say,
Oh, is it actually typo, you think?
Yeah.
Oh, okay, okay. That makes me feel better.
Yeah.
Okay, okay, awesome, awesome. Yeah, thanks.
It's like all of the time. It's related to it. It's just always involved. It's just so it's like there's some relations. Yeah, so you have like yeah, exactly. It's like the potential. Yeah, but it's like a exactly. So I think it's just the credit that gives you the so we will moderate.
Yeah, I'm in the like
And the electric field is the partial
on
kind of combines them.
Diluted on
But then it's going to be the best separate, but that's okay. Then it's
I'm
to wait, right? And then we also so it's you're most not to the limit where it dominates where it's just like a way to practice both fields.
Oh, you.
I'm not think that it's not anything about
Yes.
that makes sense.
And you quantize that.
we were discussing even before that we don't have
Yeah, exactly. That's back to like these nodes.
Yes.
Take this version down.
I figured that the present was so
Hamilton was more towards him of saying that look, okay, you can cancel. This is like big argument you just throw it. And some of the terms, but clearly this and all this relies on. That's the point we wanted to make. And then clearly we need to sharpen it. I think maybe Marit wrote it a bit fast, and I didn't think it was but I think in the end, I think really what will happen is some kind of text that is combination, a competition number of molecules. These things we don't know exactly, but I think the piece now has many modes. Silver is fine, we just need to be.
no, we need
When we saw it was all the time. Yeah, I think it's also I can see a new papers pop out now where I think it's a good comment. Just to say, we will
So, how is it going? Anyone finished? Anyone finished? Anyone finished? Because the hour is coming to the end. So, in the interest of time and that you actually have a break, because yesterday you did not have a break, I dare to interject now and show you the result. And I think if you did not manage, you can try to do it also in another time, because it's extremely instructive, at least for me, to do this calculation. And I know it's not so easy. That's why more people involved makes it usually easier. But it really shows something very, very important in QED, or in this case, non-relativistic QED. because it shows you, as you see here, just where's the pointer? Shows you here, first of all, that you get this. I mean, this is essentially the same as we did yesterday for one mode and one particle. That you here have a effective coupling strength that basically sums over all modes. And you see again, it will act like a mass, right? Now, you immediately see that you get something like a new mass, a renormalized mass. So this is the mass you start with. Usually we call it the bare mass M, and it gets changed. Now, this is just a model, right? It's 1D, a few 1D and some undefined modes, right? We just say some modes, some coupling. I don't make any other statement, right? Because this result is generic, right? You can now choose any mode structure you want. You can also, you find the same result in 3D, in 2D, it's all the same. But the important thing is we can for 3D and for free space, right? Free space has this thing. This is actually another way to see relativity is a representation of symmetries. This is always fancily called a representation of the Poincare group and blah, blah, blah. But what it basically just says is our basic theory should not depend on direction, position, how I move, whether I'm moving forward in time, backward in time, blah, 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 blah. This is all encapsulated in Poincare symmetry. It's a very logical thing to, and it just sounds more fancy. But in the end, you just say, okay, our laws should not depend on how and where I look at. Now, one very important thing is isotropy of space, right? And if we are in free space, that means these are our free space modes, right? The plane wave. And we just have now, if we think about a quantization volume of length L, we can actually do in an approximation, because else it gets a little bit hard, actually calculate this sum for a specific case, right? That's basically a change for the effective mass. And if you go into free space and you say, okay, this is all isotropic homogeneous, you can turn it into an integral over K, right? You have K3. And then again, the lambda appears, right? That I introduced at the very beginning. But in this case, what you see is, it's not that the frequency goes down, it goes up. And what you see is that the renormalized mass is proportional to M plus this cutoff. So the lambda, again, is 1 over distance. So it tells you the smallest scales, your electron can interact with the photon field, because we don't know, right? The photon field can go down to, I don't know, we don't know which size it can go down to or up to. Here, the infrared part is not a problem. It would be a problem again if we would do Dirac, but due to that we do Schrödinger, the infrared part is easy, but the ultraviolet part is a problem. So in this highlights that actually in our Hamiltonian, if we really have the full quantized field, we have a bare mass. It's not the physical mass that you write into the usual Schrödinger equation. All the mass of your particles in QED come from the photon field. So again, you have this problem. What is then the particle? The particle is just basically a cloud of trapped photons that it moves around. That means electrons and nuclei are the first hybrid light matter states that are hybrid light matter particles that we have. They are not bare particles. So everything that we do is essentially polaritonics from the get-go. Another important observation is this relation, right? Because we know the observable mass. So M renormalized is the thing that we measure, right? We know its value. This is fixed. So when you now increase your cup, now basically you say how many modes I take into account, right? Because what is the smallest scale? I don't know, right? But as I increase the smallest scales, I have to decrease the bare mass. The bare mass goes to 0. All its energy, all its weight, all its mass comes from that. But at one point, this relation doesn't hold anymore. And if
fundamental electron mass and proton mass that we read in textbooks, are those actually normalized by photons?
they are, if you believe QD, pure photonic contributions. They are basically just, in full QD, you have different contribution, but it's essentially just a photon cloud that you carry along. That's the basic mass that you get. And actually, that's true in all fields of physics. Gravitation, blah, 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 blah. It's always the same. Just think about a particle, a point particle with a mass. That's a black hole. The same thing is, think about the point particle with a charge. That's that. That's a white hole. It's always the same. The self-interaction is there the problem. And that's just another expression of these problems of these distributions. So here the issue is really fundamentally in physics. We use the point particle concept, but it's really, really not a good concept. But we don't know how to go around it. Nevertheless, we can do computations, and we will tell you how to interpret this to make it practical, right? Because at this point you could think, but then, damn, I cannot, which cutoff do I choose? And actually for the dipole approximation, it's even worse. Because if you plot this here, it should come invalid syntax warning. That's probably my problem. Where is it? This is the important one. If you namely plot, we know we have an observable mass, and if you assume we do the dipole approximation, I will explain in a moment what the dipole approximation is. But again, it's basically just saying we ignore the dependence on position, not of the photon field, so not of the modes, but of the coupling, right? It's a dipole approximation. It's not a statement about the modes. It's a statement about the coupling. The modes still have all the spatial information you want. So if you take the dipole approximation, that's true for any theory. In dipole approximation, you run into a Landau pole that it's called, where your theory breaks down, where you suddenly need to have imaginary masses. And it's a well-known result that relativistic, non-relativistic, again, any theory in dipole approximation is not renormalizable. So here you see that the theory is not renormalizable because it breaks down. The sad thing is QED itself has the same problem. There is a scale that is so high in energy, it's called the Planck scale, where then also the same issues appear. So they're at least full QED. In non-relativistic QED, we don't know. But this is very, very important to understand what you're doing different to quantum mechanics, right? We work with bare particles. You choose the scale in which you interact with the photons, and that sets you how your system behaves. And it again tells you what we call light and matter, at least from a theory perspective. I don't know. This result is not new. It has been already obtained actually the 30s or 40s. It's in some obscure PhD thesis of a student of Kramer's. Anyway, in general, this is a generic statement, not only in dipole approximation, but also in full minimum coupling. This one goes to 0, and this one becomes very large. And hopefully, if this goes to 0, the photon mass equals the observable mass, but we don't know. So you have to have a cutoff. Markus will talk about it from the math side, why it appears. There are math reasons as well. So if you have a physics problem or a numerics problem, there is always a math problem connected. If you disregard the math back there, you will not understand where the issues come from. Because specifically in high energy physics, instead of saying where the problems come from, they invent new words, which are good for a specialist like renormalization group flow. We have no idea what it means. That's exactly this, right? Because it's very simple. Yes.
Problem here also something to do with us doing a continuum limit in the end to analyze it, Because I should need a finite number of K modes essentially. Like my universe is not infinite.
No, it would be in QED, but not in non-relativistic QED, because that would be the infrared cutoff. So the discretization, that the continuum is not the problem, it's the ultraviolet part. Of course, you could say the continuum of real space is the problem, but not of K space. And there are a lot of mathematical interesting results, because I cannot go into detail, but it's not only this problem. So there are a lot of interwoven issues there that appear. All right, so particles are not bare particles. And the photon modes need to be regularized. So I just put there a lambda, a cutoff. Markus will also talk about this, how the mathematicians call this. But that is exactly what the high energy physicists do as well. They say, let's look at a scale. And here you say your scale. You say until which size, your submicroscopic size, you think it's important. And as said, in non-relativistic QED, there's still the hope that you can just let the scale go to infinity and still get the right result, at least for bound state systems. We don't do the next tech notebook because we run out of time. But what you would see is you can do the very same calculation with very many electrons. And you see this breakdown, this Landau pole, where this dipole approximation with the continuum of modes breaks down, depends on the number of particles. It's not a single particle problem. This is also, again, confusing in a lot of literature on high energy physics. It's always single particle renormalization. But if you do solids, molecules, ensemble of molecules, solvents, it's the number of particles that gives you new physics. So it's not a rerun of high energy physics. It's much, much, much more because it's much richer. All these results depend on how many particles you have there and which charges they have and which masses they have, or bare masses in that manner. One thing that you might have also realized, your wave function, in this case, you could still calculate it analytically, and you have a lot of modes. And you can imagine, if you want to represent a continuum of modes, you cannot even write down a Platonic wave function. So I have no clue how to write down, I mean, even like as symbolically. Well, how do I write this down? I don't know. You can think about the discretized one, yeah, then the discretization goes to infinity. So even a single particle wave function with a photon field is impossible to solve. Impossible. It doesn't work. That's, of course, good news for anybody that does many-body theory, because that's also why in high energy physics, we never talk about wave functions. Good. They have also different reasons. They always talk about scattering matrices, Green's functions, due to exactly that reason. You cannot even write it down. One thing that I need to stress, and I'm sorry to go a little bit over time here. One thing that I need to stress is on this level of theory, with a continuum of modes, a cutoff, bare masses, everything minimum coupling, you need to, because I now talk everything just about free space, right? Where's the cavity structure? Yet there is no cavity structure because you need to describe it as part of the system. So you put your mirrors there microscopically. Why do I say that? It seems like a terrible idea to do. I hope that you understood, or at least I convince you, say, because it's very hard to understand in detail, but at least I hope that I delivered the message that the coupling between light and matter depends on both sectors. So if you now say, which is often done, say in quantum optics, to say, oh yeah, a cavity is basically just changing my boundary conditions, or I change by hand somehow the mode structure and so forth and so on. It's a very, very, very dangerous route to go down, at least if you do non-perturbative theories and you do not want to break the gauge conditions. And remember, the gauge conditions are a consistency condition to guarantee local conservation of charge, local conservation of momenta, local conservation of forces, and so forth and so on. And once you start to play around with this, you can do it, but be very, very careful. Markus will also show an example where you see that all hell can break loose, right? If you just change boundary conditions, if you just change the mode structure by hand. So, but this brings us into a little bit of into a corner, or we're in a little bit of a pickle, because I mean, cavities, like for instance, Fabry Perot cavities are macroscopic objects. So how do we treat them? Right? It's completely ridiculous to treat them with from first principles. Now, there are some tricks that one can play, like orbital free DFT and stuff, but I don't go down this road. There's a much easier route. And that's the long wavelength approximation. And I hope that Mark will also briefly discuss this, specifically in the context also how to take then the continuum of modes into account and blah, blah, blah. I will not touch this. Maybe only like a short word would be fine. Maybe just a brief comment. You don't need to put any slides because I will not talk about how you then bring this together with known methods, blah, blah, blah. But the dipole approximation does something. Of course, it's an approximation. So you break things, but you break things in a controlled way. You lift all these local conservation laws to global conservation laws. So you cannot, on the scale where you apply the dipole approximation, resolve these local conservation laws, but at least you're safe. You know that you break them in a very specific and simple way. And the basic assumption is your system, when we talk about, say, molecules or atoms, or at least not an infinite solid, is somewhere localized in space. That's the definition of a ground state. It's exponentially localized. That's equivalent of saying I have a normalizable eigenfunction. And that sets you a scale. And if you choose the cutoff not too high, and if the modes you're interested in are not too high in frequency, then you can basically say, well, I couple everything to the center of charge and I just choose my coordinate system to be in the middle. It's basically saying for what the particles are concerned, this is roughly 1. A word of warning, the wave function never gets 0. The meta wave function never gets 0. So there is always a tail that feels that this is an approximation, right? So the idea that you sometimes read, again, specifically in the quantum optics literature, to say, okay, it's 0 far away, it's never 0, else you violate basic quantum mechanics. So there's always, irrespective how small you are compared to the wavelength, there's a small error. But nevertheless, it lets us do one thing. Let us do the following. Due to no longer have here the dependence on the position, which says we are no longer coupling to the local phase, we're only coupling to the global phase, that avoids a lot of uncontrolled problems. You introduce, of course, an approximation, that's clear. But you will learn in the afternoon, now, no, sorry, it comes in a moment. You will see on Thursday, the velocity, this is called the velocity form, how this is used, because it has a very nice property that the original Pauli-Fierz Hamiltonian does not have. The original Pauli-Fierz Hamiltonian does not have translational and rotational invariance in free space, because at least the subsystem of the meta, because you have to shift meta and photons together. That means if I now would like to use the Bloch expansion as we do in condensed matter physics, which is an expansion of a periodic wave function of meta, this doesn't go together with the Pauli-Fierz Hamiltonian. That's a problem. But it goes together with the so-called velocity gauge form, and that's what ITER will use, or will show you how to use in the case of doing first principle simulations for extended systems. There is, since we did now an approximation, we suddenly have again more freedom. Before, everything was fixed. We couldn't do anything. That was our theory. That's it, that's it, that's it. That's our starting point. We cannot change it. But now we made an approximation. Now we suddenly have some freedom again. And there's a unitarily equivalent form, which basically does 2 steps. It takes this unitary transform with the total dipole of all the electrons and all the nuclei, and then it swaps somehow the photon coordinates that I don't go into detail. This you find in a lot of books, or not books, in a lot of papers. And you find a unitary equivalent form. This is called the length gauge. And you see it looks very, very different. And suddenly you do no longer couple to the momenta, right? Like before. Now you couple to dipole. Again, I did not do much except of a transformation of a unitary transform and swapping of what I mean with creation annihilation operators for the photon field. But under the hood, a lot of things happened, because obviously this looks very weird, right? This is no longer translationally invariant in the space of meta, right? If I shift everything, this one this is not matter, right? This is no longer translation and invariant. So what went wrong? Well, you did something, you mixed again light and matter. Remember, this is now actually a different gauge. This is called the Pauli-Fierz gauge in the dipole approximation. If you use Pauli-Fierz beyond the dipole approximation, be very careful. It's very unclear whether it's mathematically sensible. But at least in the dipole approximation, they agree. But it's very important to realize that here now, the photons are no longer photons. I will come to that in a moment. And you immediately realize, yeah, where did the original translation symmetry go, right? Because here I can shift everything. Everything is translation invariance. Where did it go? Very simple. Again, light and matter was mixed. The translation invariance goes along R plus Q. Now Q and R, this is a little bit light, this is a little bit matter. So it's again mixed. And you will understand what this term means here in a moment, because I introduced it already before. But what I did here is I discretized already the continuum. And now, again, as I said, you don't break the local conservation, you lifted everything to to global conservation laws. And now you can do things like Mark will show you. You can calculate actually real geometries, real cavities, real structures, and get all these parameters from first principles. And you don't run the risk of violating basic laws. This is not the solution to everything, right? Because clearly this is a dipole approximation. It will not work on all scales. So you have an issue here, but at least that's one of the standard points that one starts with. And this one you get will be discussed in the afternoon, how to get these input parameters. And you immediately understand, if you think back to the macroscopic Maxwell's equation, what these terms are, right? Actually, the macroscopic Maxwell's equation was, again, right? All the time we play this trick that the Maxwell's equation has very different forms. So we started out with standard Maxwell's equation, and we wrote it in Riemann-Silberstein equation, then we wrote it in vector potential form. Now, and then we also did the macroscopic Maxwell's equation. Here they reappear, right? Rightfully, this a different form. And what you see here is the E field is D minus P. That was what also classically in macroscopic Maxwell's equation is assumed, right? This is just a bookkeeping argument. D is the displacement field. And now you see that the displacement field is actually given as Q. So these are no longer photons. These are displacement excitations. These are not photons. This is a different thing. And you have the polarization. These are also photons, actually. It looks as if it would be matter, right? Because there is an R, but they are photons. They are bound photons. This is a division of your photons into bound photons and free photons. And you immediately realize this is just E squared and B squared in this displacement field representation. So that means after this gauge transform, and this is a starting point that you will see also very often in polyatomic chemistry and for finite systems, because there you don't care so much about this translation variance. Again, you see the problem if you would like to apply this to a solid, you would now need to calculate your Bloch state with respect to this new coordinate, Q minus R. That's a little bit hard, or you can do it. We did it, but it's not so convenient. And also if you now calculate the number of photons, this is not A dagger A anymore. Similar to the first notebook, you have to keep track what type of transformations you did, because now you have to go back, and actually the photons will be basically a sum, essentially, of this term and of that term. So both contribute to the number of photons, the free photons and the bound photons. And one last thing before I stop. We have seen that the Coulomb interaction comes from quantizing the light field together with quantizing the matter system. And it takes a while to go through all of the steps, but essentially what you do is you make sure that the transversal modes and the longitudinal modes of your vector Laplacians agree with the modes of your scalar Laplacian in a specific way. This is a different way of seeing gauge conditions and blah, blah, blah. So, however, now, if you now from a cavity get changes in the transversal degrees of freedom, you automatically change also the longitudinal degrees of freedom. How much? We don't know. This is again something that Mark can tell you. This will depend on the situation you're in. But in principle, your longitudinal interaction changes. Again, just this thing here, the usual free space one, you can just write here as 1/k². Here again, the exponential comes into play. And this is basically the inverse of the Laplacian. It's not only the inverse, it's the inverse of the scalar Laplacian, but from this you get the inverse of the vector Laplacian. And if you get the vector Laplacian, if you change the vector Laplacian, you also change this. In other words, if you change transverse, you change longitudinal. Again, it depends on the situation, how much. Again, you can do this in dipole approximation. And that's, again, just a word of consideration. Usually in the Fabry-Perot case, these contributions will be minor, so you can ignore it. At least we believe like this. But for instance, if you're close to a surface, they might be important. Yeah.
Mean that I change my Coulomb interaction with the unitary transform in this case, right?
No, but if you change the mode structure, you should reevaluate what happens. Because the dipole approximation, because you make a dipole approximation on the side of the transverse parts, you then choose new eigenmodes, and these eigenmodes lead then to your new frequencies, blah 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 blah, to model basically. Because in this case, you do not need to treat your cavity explicitly. The cavity just becomes a change of the photon modes. That is much easier, right? That was also done in quantum optics. But then, and I'm not saying one needs to do it, and I'm saying in principle, you need to think back because the Coulomb interaction, there you didn't do the dipole approximation, right? Also, don't do a dipole approximation of the Coulomb interaction. There is no Taylor expansion of an operator. Doesn't work, does not work, does not work, never, ever. Really, never, ever. So one can think, however, what would happen to the Coulomb interaction if I now would really have changed this mode structure? And so you can just go through the math and you will see the appearance of things that look similar to like mirror charges or so forth and so on. Yeah.
So in like the theory of electromagnetic environments, you also have these ideas of mirror charges and boundary Green's functions. Is that meant in this direction?
It's meant in this direction, yeah. Just from the perspective that these mirror charges and Green's function, they are just, that's a Green's function. The inverse of the Laplacian. And the inverse of the vector Laplacian is the Green's function or the dyadic Green's function in free space. So if you change the dyadic Green's function of free space, you change also this one. So you can reinterpret, as always, there are luckily enough different ways to talk about the same topic. But this is basically just saying you might need to consider this depending on the situation. But again, usually, Fabry-Perot, we are relatively happy. In principle, for ab initio, this is not a problem, right? You change the Coulomb kernel, at least for things like, for certain methods. For other methods, it gets very hard. All right, but this brings me to my end. Sorry for getting over time. And Markus will tell you afterwards, after the break, a little bit.
Assume at 11 then.
Yeah. Yeah, we started 11. He will tell you a little bit about the thing that I swept under the rug. I always said, okay, there's a math issue. I always said there's a math problem, blah, blah, blah. And he will try to elucidate a little bit because there's a lot of details. Okay, thank you so much.
Ruki introduced the whole setting, the quantum mechanical QED setting with this Pauli-Fierz Hamiltonian. It's my job to add some mathematical considerations to that. So I'm the math guy of this group here. And I try to solve out the math problems. Sometimes we're successful.
Mostly not.
No, but I will show you, although there's a lot of, how Ruki likes to say, snakes in the grass, that doesn't mean that problems cannot be resolved. And there are actually settings that are even mathematically beautifully and well-defined, which is always very nice. But it doesn't mean that the whole theory is always well-defined. And I think it's time to go back to this Dirac quote that Angel brought yesterday, and that's somehow always at the center or at the beginning of our field, it seems to me. And the funny thing is, like Dirac says something, the underlying laws are now all well-defined and well-known. But if you look at them mathematically, they don't seem so well-known at all. So of course you can write down a Hamiltonian, but paper is very patient, it won't complain. But as soon as you asked questions like, yeah, but is there a ground state for this Hamiltonian? Is there a well-defined spectrum? Do we find excited states? Well, then you could see that in many cases, this is not so well-defined after all. And then usually math jumps in and tries to sort out the problems. And this doesn't mean that it only sorts out the problems and there's nothing to gain from that. Because I think that if you solve the math problems, it also usually means you can avoid computational problems from the start. Or, which would be even better, you can find maybe new computational methods or even new theory methods that you can then try use and solve real world problems. So that is very nice. And I think like the whole history of theoretical physics, nobody will doubt that math plays a central role there.
Nowadays.
So I think it's very important to also take math extremely serious and try to do it right. So I try to show you some of these topics here, and I hope to convince you that this is interesting. So here's the learning objectives of this small part in the next hour. First, we introduce just when we are having operators here all over the place, and with the examples of the position and momentum operator, I want to show you on how to understand unbounded operators, how they arise naturally in quantum mechanics, and how self-adjointness, that is always another important condition, and I will tell you why, how this relates to boundary conditions. And then boundary conditions were mentioned by Ruki several times because it's important that they match, so that the operators that act on the light part of the system and those of the matter part of the system, that they agree, and that mainly means that they share boundary conditions. Then we should get familiar with the photonic Fock space, because this is the more complicated space, I would say, because it has potentially infinite number of particles. And how to introduce not only creation and annihilation operators, but also a regularized version of them that is mathematically then well-defined, and that already relates to the cutoffs that were previously mentioned. So this is nothing that is just present there in the mathematical formulation. It also always shows up in every formulation of QED that you need to introduce those cutoffs. Then for the Pauli-Fierz Hamiltonian, or for a little bit simplified version, I want to show you what it takes to have it actually as a self-adjoint operator on a nice domain that is bounded from below, because that's very important, as I will argue. And then if there's still time, there's a little epistemological part here where I want to distinguish theory from model. That relates very much to what Angel said yesterday. And I want to try and characterize ab initio theory for you, because it's in the title of the whole school. Okay, first let's start with very basics, quantum mechanics, position and momentum operator. And usually every quantum mechanics course might start something like this. There's a basic relation between those operators on a given Hilbert space. So you think of operators, yeah, there's something like matrices acting on a vector space. You can write here this commutator, which just means replacing them and subtracting them. And then this should give unity. So, and it is like at the starting point of like Heisenberg developed quantum mechanics. This was at the starting point, really. We need those operators with that are not commuting. That's the special thing about quantum mechanics. And this is the basic constitutive relation here. So there's something interesting to learn from just this very simple relation. Assume the dimension of our Hilbert space, our vector space, where these operators act on, is finite. Okay, why not? Finite dimensional space. like 3, 10, 100 dimensions, maybe a billion. Then also the trace, of course. I mean, every operator on a finite dimensional space is bounded, so this trace must be finite, obviously. But now remember that the trace is cyclic, so you can always move parts from the back of the trace to the front. Apply the trace, also the trace is linear. Apply the trace here, you have the same thing here. It's 0. But apply the trace to the right-hand side, the trace of unity is the dimension. So 0 equals the dimension. Oh, interesting. Okay, that's a very small space, right? So what happened? Apparently, the basic condition here, that this trace is finite, is not true. And what actually stands here is infinite minus infinite, and that is not 0. So what we learn from this extremely simple math exercise is the Hilbert space cannot have finite dimensions if we want to have the canonical commutation relation. That means in every approximation on a computer, in a smaller Hilbert space, where we want to represent those operators, in some models we don't even want to represent them, but if we want to make a continuum model, we want to represent them. We go to a basis set, we always make a mistake. Okay, it's unavoidable. It's not possible to fulfill the canonical commutation relations in finite dimensions. So said again, there's no possible representation of these operators on finite dimensional Hilbert spaces. And there's a funny inequality that we like to stress. Quantum mechanics is not linear algebra. So even though we use, this form of quantum mechanics, sorry, you can write down a Hamiltonian for a model system and it makes sense and everything is nicely defined, but not this continuum quantum mechanics with position and momentum operators. This is not linear algebra and it will never be. So one needs more than linear algebra, and the theory that lies behind all of this is called functional analysis. It's the theory of function spaces and operators on them and spectra and all this funny stuff. So, and we will go a little bit deeper. So now that we know that the Hilbert space is infinite dimensional, we have to talk about the norm of operators, and operators don't need to be bounded anymore. So this is the definition of the norm. You just apply it to any vector, you divide by the norm of this vector, and you look for the smallest possibility like this. This is the operator norm, and we look again to our favorite operators, position and momentum. Now, there's this nice relation that you can easily derive from the canonical commutation relation, that the P is a, what is it? I mean, it's a derivative, right? P is a derivative. If you apply a derivative to x to the power of n, you get n minus 1. And you get down an n. And the IH bar is just in the basic definition of the P. So this is actually how you see that later the P will be a derivative operator. Because first it's not, it just fulfills this basic commutation relation. Okay, that's how you start. Okay, so we have this nice equation. Now we take the operator norm of this equation. So on the right side, you have this. I mean, those are just constant, you pull them out. On the left side, you have here the commutator. You use the triangle inequality. You use the inequality that you can evaluate the operator norm separately here. You separate 1x from x n minus 1. There's a 2 because it's 2 terms. And now, obviously, you can cross out this norm. And in the next step, you have the norm of x times the norm of p is bigger than n. Oh, but there's no need to choose this n especially small. We can choose this n any number. So you see, one of those operators, or both, have to be unbounded. So not only that our Hilbert space has to have infinite dimensions, those operators have to be unbounded. And the unbounded operators are the more difficult ones because it means not every vector is necessarily in the domain of those operators. So you cannot apply those operators to every wave function you can imagine. And that does not come as such a big surprise if you look at the representations of those operators that I will talk about now. So the usual, and I will not tell you something surprising here, the usual representation of X and P as unbounded operators on a Hilbert space can be these. So I say my wave functions are functions on space, one-dimensional, three-dimensional space. And the position operators works like just by multiplying the position, every position to the wave function. And the momentum operator acts as this derivative for any psi. But now you already see the problem. Not every psi here can be, it's differentiable, right? Not even in a weak sense. And that is exactly the problem. The domain is smaller, or in other terms, the operator is unbounded. This representation is called the Schrödinger representation. And interestingly, it can be proven that it's unique up to unitary transforms. So in a way, up to unitary transforms, this is the only possible representation. So you know that position and momentum operators that are only defined with this canonical commutation relation have to look like this. And what are unitary transformations? Well, the one that you can, of course, think of is the Fourier transformation that just replaces position and momentum. Then, yeah, you have, then momentum looks like position and the other way around. And that we use all the time, because as you saw, I think also you wrote sometimes in K-space. Sometimes we like to go to K-space to formulate things, and it will also appear later here. Okay, now the next thing we'll talk about is self-adjoint operators, boundary conditions, and all that. So we use different boundary conditions. First, we take one-dimensional space, wave function in one-dimensional space to keep it simple. We take the whole R line, so there's no boundaries at all. So our basic domain here is all L2 functions where this derivative, it's usually meant to be the weak derivative here, but that's not that important now, is finite. So think about its differentiable functions for sake of simplicity. And now we take this inner product with another vector, and you can use partial integration to move the derivative to the other side, but you get, of course, boundary terms, okay? Now, the good thing is, do the boundary terms vanish? Okay. Do the boundary terms for L2 functions always vanish? Who would say yes? And who would say no? Yeah, the answer is no. So, because what you can do is take a function that looks like a Gaussian and then move a few kilometers and then make a smaller Gaussian and then move double as many kilometers and take a much smaller Gaussian, but they always have the same height. And you see, there's no need that a wave function that is in L2 has to go down. You can show that such a wave function can have a well-defined L2 norm. The good thing is we also have the second condition. Because I told you these Gaussians have to become smaller and smaller, and that means the derivative gets higher and higher, and they will never fulfill this property. So it's a very hard math exercise to show that these boundary terms go to zero. I mean, we always do it because we know it after we did this once, but one should know what you do. So you cannot say that this goes to zero if this is the only condition. Only with this extra condition, those terms go to zero. But we have the condition. We are on this domain of the operator. So indeed, we have the operator on the other side. And now for physics persons, this means, the operator is self-adjoint, right? I mean, if the inner product, you put it to the other side, isn't that self-adjoint? Is it self-adjoint? No, that means the operator is symmetric. Okay, I have to define self-adjoint for you. And for this, I have to define does it mean to have the adjoint of an operator? And the adjoint of the operator is, so that's how it acts. You take any phi in the domain of the adjoint that has yet to be specified. Okay, so all the operators that fulfill this condition are in the domain of the adjoint. The adjoint applied to the vector gives you this psi. And how does it work? Well, it's defined with this relation. So you can use psi here instead of, well, moving p to the other side. So it looks exactly like this, but the extra ingredient here that is very subtle is that this domain could be potentially larger than the domain of the original operator. And that's very hard to understand. That's why I will show you an example on the next slide so you can really see what this means. But any operator that fulfills this condition here is called the adjoint. And then the maximal domain of it, so to say, the maximal domain here is the domain of the adjoint operator. And only if the adjoint operator acts like the original operators and the two domains agree, then this operator is called self-adjoint. So what you should remember is a self-adjoint operator is a symmetric operator that has also the same domain as the previous operator. Okay, and I think with the example, it should become clear why this is not totally trivial that it has the same domain. But of course, you know that on the real line, the operator is actually self-adjoint, so there's nothing wrong with this example. The momentum operator is self-adjoint on the whole line. But now move to hard walls. Okay, hard walls means we have a bounded domain and the wave function is 0. So you see, like in the conditions, still we have this condition of a finite derivative here, but we also have these extra conditions that the operator goes to 0. Again, wave function, sorry, wave function. Again, very careful. This might not be sensible. I mean, what is psi at the point? L2 functions cannot be evaluated at points. But luckily, this extra condition makes it possible to evaluate them at points. Again, a very non-trivial result that in 1D, wave functions that have a finite weak derivative are actually continuous functions, or almost everywhere continuous. So good, we have the same thing as before. Let me move back. I mean, the boundary terms obviously vanish. Now it's 0 to 1, but I mean, the thing is 0 at 0 and 1, so the boundary term goes away. But why is it 0? Yeah, because the psi, right? It doesn't matter what the phi is, but since the psi is 0 at 0 and 1, this term vanishes. But that already shows you what happens. This is not needed for the phi. The boundary conditions are not needed. The psi, just because the psi has the boundary conditions, the boundary terms are 0. So the domain of the adjoint operator is larger. The domain of the adjoint operator is this domain here without this condition. Okay? So what we just showed is that P is not self-adjoint. It's symmetric, but it's not self-adjoint. And it's a general rule that the domain of the adjoint operator can be larger. And that should show you something about physics. Now, I mean, this is a purely mathematical argument here, but there's actually some physics to learn from that. After all, these operators are the generators of translations, right? The momentum operator is the generator of the translation. But can you translate? No. I mean, if you translate by 2, where do you go? It's hard walls. There's no way where you go, right? So it already shows you that there are no translations because there's no self-adjoint operator that is the momentum, so there's no translation group, and so on. It's all because of the hard walls. So is there maybe a different way? It's like self-adjoint extension or something? Can we get rid of it and this problem? And obviously, what we could do is make the whole thing periodic. Because as soon as it's periodic, we can translate by any number because we would just go in a circle and continue from the start. And that's the third example, periodic boundary conditions. So now the condition, if you work out the integral, move partial integration, then this is the condition for vanishing boundary terms. And now you see that there are many ways how to fulfill that. And these are these two equations. So as long as these two equations are fulfilled for any choice of alpha, this is 0, as you can easily convince yourself. So now the thing is self-adjoint again, because now the conditions, I mean, they are exactly the same, right? So again, the domains are the same, but do I have a unique self-adjoint operator? No, I can choose this alpha. There's an infinite number of self-adjoint realizations of this operator. I mean, the operator is, there's no alpha in this operator, right? So you would usually write down this operator and say it's defined. But no, it needs to be defined with a domain. And the domain means, in this case, boundary conditions. And the boundary conditions can have many different forms. That you can choose an arbitrary phase jump when you go the full circle. Okay, so every time you cross the zero, you collect a phase, so to say. And every realization of this operator is self-adjoint. So what you should take from this is symmetric is not self-adjoint, and a self-adjoint operator is only fully specified with its domain. So just writing down what the operator does doesn't tell you the whole physics. And it is physics that is there, because I mean, changing the phase in every round clearly is something physical as well. Okay, so that is important here. So now why self-adjoint? I promised you I will tell you why this is even important. There's many reasons. I mean, the whole of quantum mechanics is built on self-adjoint operators. Of course, you would say real eigenvalues. I want to have like measurements coming, like real numbers from measurements, something like that. So, okay, real eigenvalues. Then I think even more important, because the real eigenvalues, it's maybe not that important. Because I mean, if it's complex and there's a real and imaginary part, you can also make sense of that. It's not a big problem here. But what is way more important, every such operator admits a eigenbasis. Yeah, that's not entirely true, actually. I want you to be a little bit careful. But you need this, you have the spectral theorem, you can have your discrete part and your continuous part. So you know this eigenbasis stuff and all that you use many, many times. And then what is also very, very important in the context of quantum mechanics is every self-adjoint operator admits a unitary evolution group. So the exponential I times t times operator, usually with the Hamiltonian, is well defined. Or, like I told you, it's the generators of the translation group. So if you put in the momentum operator, you get translations. And only for self-adjoint operators, it's easy to, not so easy, that's Stone theorem, to make this a well-defined expression, these exponentials. Because remember, these are unbounded operators. E to the power of an unbounded operator. I mean, it's like e to the power of infinity. That's not so easy to make sense of that. But for self-adjoint operators, it's possible. It's a very powerful theorem that's called the Stone theorem.
A question about the eigenbasis. Is the eigenbasis always complete in the Hilbert space of a self?
No, that's why I already said, no, there might be problems. Yeah, because you have this continuous part. Just think about the Hamiltonian of the hydrogen atom, right? You have all the bound states, but then there's a whole part of the scattering states missing.
Yeah, you have an expansion or an expression of the identity.
Yeah.
So it is a generalized basis.
Yes, yes, yes. It's a bit more subtle, but yeah, you can think like that. Yeah.
Like X or K.
Exactly. X is the easier example. Take X on the whole line, and then what is the basis? There's no eigenbasis here. Okay. But maybe I should say certain self-adjoint operators admit the eigenbasis. This is clearly true. I just wrote this morning, so I was not so. Okay, now coming back to this example, each choice of alpha will result in a different self-adjoint realization of the momentum operator, kind of the same operator, but no, different operators, different translation operators. I mean, they act. This is this unitary evolution group that I told you about. But they don't act the same depending on the alpha, because you push it over the zero and it gains a different phase. So different physics. But there's another caveat to this. So take any, like with this nice realization of the momentum operator, take any wave function in the domain and now multiply it with the position operator. Now the position operator at 0 is 0 and at 1 is 1. This is maybe not anymore in the space with periodic boundary conditions, right? Because you multiply it with 0 here and with 1 here. Only if it's 0 at the 1 point, it's again in the domain. So that means you could have a problem with this commutator, because the x times p has the domain of the momentum operator, but the px has not. So the x destroys, applying the x destroys the domain of the p, so to say. So this could be seen, this can be a problem, doesn't have to be a problem. I mean, it's enough if this commutation relation is fulfilled on a dense set, it should say, dense domain in the Hilbert space. But just to be careful, if you apply an operator and then another operator, this does not always make sense, because you can be cast out of the domain of this operator. Okay, a little bit of a catch up here. Unbounded operators always come with domains that I said. Then for self-adjointness, the domain of the operator and of its adjoint have to agree, else it's only symmetric. For unbounded operators, composition and addition are not defined on a universal domain. So you have always to take the domains of the operators into account, and there could arise problems if you do that.
May I?
Yes, sure.
So adding operators does not make automatically sense.
Yeah, because you need to have a domain like for both, right? If I write a plus b, I mean, it's very easy.
Just stress this point, because this is very subtle.
Okay. I mean, I write a plus b, nice. But maybe the domain of a intersected with the domain of b is nothing. So what should that mean?
Nothing.
Yeah. So one has to be a little bit careful what operators you add. It doesn't mean it's not sometimes possible. And yeah, I mean, we have as states in quantum mechanics, we usually think about the whole Hilbert space, but not all states are the same or as useful. So, I mean, and not every operator is an interesting operator. So we have certain operators that are highly like special and that are highly more useful. And that is, of course, momentum, position, the Hamiltonian, things like that. So the domains of these operators are extremely important. And it's very important to understand mathematically and physically what those domains are, how they can be formulated, what to do with them. So this is a whole field of study, studying the domains of the operators. Yes, please.
So it seems like we have to keep track of the domain auxiliary to the operator.
Yes.
Could I also think of like the operator sandwich between projection operators? Was that not?
Yes, then of course you're restricted to where the projection operators maps to. Yeah, but
right onto the domain of the operator. Would that give the full picture, or lose something?
No, then that is okay as a mathematical formulation, but you would not. I mean, you would not change anything in these problems, right?
No.
Because then maybe you project to the domain of A and you project to the domain of B, and if you project to both projections, nothing's left except of 0.
Yeah.
Yeah.
But that would make it explicit that.
Oh yeah, yeah. Yeah, but then it could be that it's always 0. Yeah. But you're right. It's better defined. Yeah. For that, it's maybe a nice idea. Yeah. But you would not gain anything from it, I think. Okay, now let's talk about the spaces. I think yesterday we heard the spaces are the theater of our whole enterprise here. So in general, we think about, I mean, many times, and that was also in the examples here, we restrict to only a few modes, maybe even only a certain number of photons. So you cut this space somewhere and things like that. But in general, we think about the photonic Fock space as a continuum of modes indexed by these k vectors, the momentum vectors in R3. Then you have, of course, the polarization. How do we say it? We call it polarization. Yeah, polarization lambda in 1. You can say 1, 2. It doesn't matter how you call it. And one photon Hilbert space. So you really have only one photon would be this L2 R3 Cartesian product with 1, 2. And that is the usual way to write it is that is isomorphic to L2 tensor C2. So this really looks like an electron Hilbert space. So interestingly, the space for one photon is exactly the same as for one electron. It's maybe there's some, yeah, but it's good. It's the same building blocks for the whole theory, right? Now, the big difference is, of course, there's not a fixed number of photons and there will not be a fixed number of photons. So we need to build a photonic Fock space for an infinite number of particles, for an infinite number of photons. And the way you do it, because there's different ways how to do it, and that's the way how to do it separably. A separable space is very, very important concept because it means you can find a countable basis for this space. And that you use all the time when you write down things, because often you say, now choose a basis, and then you write a sum, k0 to infinity, okay? And you sum overall basis elements, projections, whatever, or coefficients, whatever. But if you don't have a separable space, you cannot do that. There's no sum that with an index that goes from the first basis vector to the infinite. But this way of constructing a Fock space, and as I said, there are others, this way is separable. So what I do is first take this one photon space, make a symmetric, because it's bosons, make a symmetric tensor product n times. So you start with 0 times, and it's just complex numbers, 1 time, 2 times, and so forth. And those you make you make a direct sum of those spaces. So the direct sum you can think of sectors, it's the n particle sectors. There's a 0 particle sector, a 1 particle sector, and so on. Every sector has its own many particle wave function that is symmetric. Okay. And they are orthogonal, those sectors. So this is this direct sum always produces orthogonal subspaces. And in this huge, incredibly huge space, there are your wave functions for the photons live. So there are photon wave functions. And in practice, if you really want to try and put this on a computer, you would, of course, replace this infinite by enough photons that you need to describe your effects. And I think in practice, those are very few, if I remember correctly. I only know from Heiko that it was 3 or 4. So and what you would try to use, I mean, you always see if your problem converges, right? So if your photon occupancy goes down almost to 0 for 5 and 6 photons, well, fine, and everything seems to be more or less good. But if you reach this wall of maximal photons, then probably it makes sense to use more photons. But as you can see, I mean, this, if you want to start discretizing this space, it will get so high dimensional. So you need to do that for the sake of simplicity, and so you can actually do computations. Okay, sorry, and we define creation and annihilation operators for these modes. But how many modes are there? There's a lot of modes. I mean, there's an uncountably many modes, right? Because any R3 value and any lambda 1 or 2 gives you a separate mode. And these modes are all sharp. So there's a K number, and it would create a delta at this K point for a photon. So in position space, this corresponds to plane waves. They have a well-defined frequency, those photons. So that is a problem. And I will tell you about this problem by going to classical physics. Yeah, a long time. So write down the Newton equation for the movement of a point-like charge, right, in an electric field. And you would say, yeah, that's easy, right? It's just the usual Newton equation, the acceleration equal m times the acceleration equals the force. And then I define the velocity as the time derivative of the position. Nothing spectacular here. And now I want to replace this by a more realistic, because the first is a point particle. But now let's say I have a small sphere, or I don't know, some object that has a charge distribution, and it's not, it's totally rigid. So you cannot lose energy by deforming it. So you have a rigid charge distribution, charge times phi of r. And usually you would say, okay, I think these are particles. I think of them as spherically symmetric around the origin, smooth. They integrate to 1. So the charge really tells you the whole charge. And they introduce a characteristic length scale, and it's the size of the particle, right? But it's all classical physics. Why shouldn't you be allowed to do that? How does your equation on the top change? Well, on the left, everything stays the same. You take the velocity of the center of this little charge, and then you need to integrate on how the electric field acts on every point of this little sphere, right? So that will be the straightforward way to formulate that. Okay, nothing happens in the second equation. I just replace x and r. Why can I do that? Because I said it's symmetric. And then you see that this is a convolution. So this integral is a convolution integral, and you write it like this. Okay, if phi is something smooth, like a Gaussian, so we go to 0 in a soft way, then this is like this mollification of this E field. So this is like a Gaussian blur filter for the E field, okay? That's just how you can think of it. And what is important to remember that there's this very nice convolution theorem that if you take the Fourier transform of a convolution, it is just a Fourier transformed charge distribution at E field multiplied. So a convolution in the on the one side goes over on the Fourier side to just a pointwise multiplication. That we will need later. So nothing very special here, just how Newton's law would look for extended charge distributions. But now, say the charge distribution, we go back to a point. So we take this Gaussian smaller and smaller, we keep the volume, we keep the integral the same, we go over to a Dirac delta. So that means on the Fourier space, this goes over to a constant function. So now the plane wave is on the, it's on the K side, on the Fourier space side. Then the electromagnetic energy of the field of such a charge would go to infinity. That's a simple calculation. Okay, compared to that, if I have a sphere with radius r and I calculate the energy of the electromagnetic field. Okay, the first is like really I should say maybe this is like one, I would say like a divergency in classical theory. So divergencies are not something that only occur in quantum field theory. They also occur in classical theory. Take a point charge and you cannot define the energy of its field. It has infinite energy. Okay, so let's not take a point charge. Let's take a solid sphere of radius r. You can calculate the energy. It's this nice value. And actually, what you get is you can calculate electromagnetic mass from the field momentum. So moving back to Newton's equation, and you get this, and you see, oh, those two equations look very, very similar. So I can compare them, and you get E equal mc square 3/4. And that was derived by Lorentz in 1904. So you might see, okay, this is 1 year early to Einstein's relation. So Einstein's relation didn't come out of nowhere. This was really in this whole study of classical electromagnetism. It was already prepared. So that I find very interesting. Just the prefactor was not quite the same. Also, I mean, it's a very special example, right? It's a hard sphere. So now you could ask, if you make the radius smaller and smaller, what happens? Well, this mass goes to infinity. And how do I save it? Well, I say, okay, now there's this mass that is in the electromagnetic field, but also the particle itself has a mass. So I could say the mass, the physical mass that I observe, that I hold fixed. So as the electromagnetic mass goes to infinity, the bare mass goes to minus infinity. It's a terrible thing, but okay. At least I can say that the physical mass stays constant this way. So this is just an example of renormalization, how this can be saved. But yeah, with wild mathematical tricks. But already in classical physics, you could see renormalization show up. If you ask, like, yeah, what is the physics of point charges? So in order to avoid all those problems, we just say we don't have point-like particles, okay? What we do in our creation and annihilation operators, we say that in the Fourier domain, we multiply this phi, that is exactly the phi from before, like the extension of my charge, so to say, we multiply it to the operators and thereby mollify, smooth out how the field operators act. So you can think of this phi as this is stamped onto the field as the field interacts with the particle. So it's really like the shadow of the particle on the field. And that's why it's called a form factor. So it's, and it's chosen, of course, usually symmetric real and yeah, some regularization conditions here. And then we define our field operator, the one that Rugi already presented. So he wrote you exactly this equation. The only difference was there was no phi. And this phi will be important to make everything well defined, but somehow this phi already showed up before. Because if this phi goes to 0 for high k, what does it mean? That's of course the UV cutoff. If it goes to 0 for small k, that's an infrared cutoff. So you can use, and you can do many ways. I mean, you don't have a hard cutoff. You can have a hard cutoff if you just take the phi as like constant and go to 0. But it usually would take it smooth, and I think you need to take it smooth to have some differentiability conditions and stuff. So you have many different ways of introducing a UV cutoff or an IR cutoff. So this is how, through this making the field operators well defined, so they don't act like delta distributions, how you make your or how you introduce cutoffs already into the theory. So they are there from the beginning like this. Yeah.
So these regularization factors essentially appear in the same form as a mode function would. Is there a connection?
No, the mode function is still there.
Yeah.
They are appearing in the same form, but on the meta side, I would say. I mean, you could absorb them in the mode function maybe, and then yes, but
it's like the coupling depends on k.
Yeah, it's. I mean, they don't appear. They would not appear if you have.
It's really the coupling.
Yeah, it's just in the coupling. So that's the difference. If you have only the field Hamiltonian, they would not appear. Yeah, that's the difference.
But really saying then, to which scale do I allow how to couple?
Mm-hmm. Okay, now we combine all these things. We take a Hilbert space for the meta part. Now I discuss only electrons. You could include the nuclei here. It doesn't change the theory really, just makes everything more complicated. I only look at, and often it's presented like that, only electrons. They are from an antisymmetric Hilbert space of n fixed number of particles with this one particle Hilbert space. The same one particle Hilbert space is used for photons. You make the symmetric tensor product of n particles, of n photons. You add up the n photon sectors to infinity. That gives you the full Hilbert space. And this is that one, particle sector, field sector. And we'll see how the time is if we want to look into notebook 6. So notebook 6 shows you an example where the boundary conditions for the field part and the meta part don't match. So like this mode function here is deliberately chosen so that it destroys the boundary conditions. And then you see what happens. And what you will see, or what you can see, is that conservation laws are not fulfilled anymore. And of course, by applying just the field, you get thrown out of your basic domain for the meta part. And that, of course, is not good. So you cannot expect to have the correct physics with that. And that means if you combine separate matter and field parts, make sure they really fit and everything works out nicely. Okay, that is nothing new. It's just the same operator as before. The only difference is that now my field operator here includes this form factor from before, but you don't see it because it's hidden there. And I only consider electrons. But apart from that, it's exactly the same of what we have seen before. And you see that on the top two equations is, I think, how Ruki wrote it. And on the bottom, I just write it out as two different parts of the Hamiltonian. And that will be important in what comes. So there's one part of the Hamiltonian that is totally like for itself. So there's no coupling with matter and fields. So we have this matter part, just the kinetic Hamiltonian on the electrons. Then I have the field energy here. And then there's this part of coupling. And the first part is coupling between the field operators and the matter operators. And the last part is the Coulomb interaction. And Ruki showed you how this arises from the interaction with the field as well. Although only matter parts show up effectively. Okay, so we have H0, not coupled, and H1, the coupling. Why is this division sensible or important? Because you see that the first Hamiltonian has a very special structure. This is, of course, p squared. So, and this is A dagger A. So those two terms have this structure, operator, dagger, operator. And it's much easier to show for such an operator that it's self-adjoint, for obvious reasons, right? I think. So you don't need to show so much. So somehow this operator, if it comes to self-adjointness, you can already write the check mark. And this will be important because there's a whole and beautiful theory developed by Toshio Kato in the 60s, I think, 50s, 60s, about perturbations of linear operators. And perturbations is not perturbation theory as in quantum mechanics, but it says, take an operator as your basis, that's the H0, and add another operator. It doesn't have to be small, but add another operator that fulfills certain conditions, then your mass setting stays the one of the original operator. And that is very, very, very practical because usually you will have operators here like the Laplacian that are always the same ones and that you understand very well. And then you can add perturbations of this kind that can look super complicated, but nothing changes in the mass formulation. So, and that I will show you as a beautiful theorem. That's the Kato-Rayleigh theorem. So if I have this H1, the perturbation, as H0 bounded, and what this means is, this H0 bounded, is that the domain of the H0 is in the domain of the perturbation, and that there are constants, positive constants A and B, such that for all wave functions from the domain of the original first part, the following inequality holds. So the norm of H1 applied to any wave function from the domain here, there should be an estimate of this kind, okay? So this helps you because sometimes it's not so hard to show this inequality with the operators, for example, that we have. Because that means the theorem is if it's, so that was not the theorem, that was the definition of H0 boundedness. But if H0 is self-adjoint with some self-adjoint domain, and H1 is only symmetric, and symmetric is extremely easy to show. So there's not much to show for symmetric. But self-adjointness is hard to show. So if one part of the Hamiltonian that we already know, like the Laplacian, yeah, we know it's self-adjoint, and the perturbation is symmetric and H0 bounded with a relative bound of smaller than 1, so this A can be chosen smaller than 1, then the total operator is self-adjoint on the same domain. So that means that's why it's called bounded. The domain doesn't change. And further, it's bounded below if the original one is bounded below. So that's extremely useful because that we apply to Pauli-Fierz Hamiltonian.
Just make a comment?
Yes.
Why is this so important? Also physically, right? Because states with finite kinetic energy and finite photon energy stay finite. If you would change your domain, this would be awkward.
Exactly. Yeah. Yes. I mean, the Hamiltonian tells you about the energy. Yeah. And then now we change the Hamiltonian, but you don't change it in a really extremely
what was finite
disruptive
before
way.
is still finite.
Exactly. Yeah.
Because there are cases where this happens, where you get to a completely new domain and you basically change completely the physics. It looks very like you add just a small thing, but the domain completely is a different thing. So what was physical before is no longer physical then. And that you do not want, right?
So the question is, can we apply this to the Pauli-Fierz Hamiltonian that I showed you? And I already showed you the H0 and the H1 part. So the H0 is the matter and field parts independent of each other. The H1 is the coupling. And we just need some regularity conditions on the form factor that are not so problematic. We need that the external potential, if we have one, is such that it allows a ground state if we don't consider photons. Well, that's a very natural assumption. We have to be able to bind enough electrons. In the Hamiltonian.
This is full minimal coupling.
Yes, and where's the A squared?
It's here. There's an A, there's a square.
You're missing it, yes.
Oh, well, maybe it's on the right. No, it's here. That's the A squared.
No.
No, maybe.
Yeah, you would add it on top.
Yeah, I would add it on top.
The H0.
Yeah, thank you. Very good. Yeah. Very good comment. I have to repair my slide. Okay. So we need some regularity conditions on the form factor. We need the external potential such that it can bind enough electrons. And we need to have actually the coupling constant small to apply Catorelli. Now that seems to be maybe a problem because how small is small? But for a first proof, this was enough. So that's the usual proof you find in the literature. And then, I mean, you have to look at those years. I mean, it's the Pauli-Fierz Hamiltonian that has been around since the 60s. And only since the 2000s, we know that it is even self-adjoint. It's catastrophic, actually. And Fumio Hiroshima has a proof where you don't need this condition on E. But it's quite recent. And it's still active research, this field. So, but the good news, the Pauli-Fierz Hamiltonian, you can show it's self-adjoint. So it has a unique time evolution, a well-defined time evolution. It's bounded from below. So you can use an energy minimization problem to find the ground states. That's the basis for DFT. If you include infrared cutoff, you don't need to include that, but if you include it, you even have a gap between the ground state and the continuum. So a small gap opens and you're not with infinitesimal energy already in a scattering state. You have finite lifetime for excited states. Now this is the continuum. So you have this interpretation of spontaneous emission for those excited states. And that means we have fully non-perturbative and mathematically consistent ab initio quantum theory of light and matter. So that's the good news. So in this case, with this Pauli-Fierz Hamiltonian, it seems like you can make everything well defined. The only extra element was this form factor compared to what Ruki told you. So it's possible to do rigorous math on that. But the removal of UV cutoffs, so in other terms, getting rid of the form factor remains largely unsolved or mostly unsolved, or totally unsolved, maybe. Okay, so you still need this form factor. Okay, I will use the last 10 minutes. Yeah, exactly.
A little bit more because it's up until 15, right?
Oh, that's perfect. Yeah, please.
Those finite lifetime movement excited state of the
There are no excited states anymore.
Yeah, it's not like this is excited states. This is like scattering states.
They all become resonances, as you know, right? They don't live forever, but they will decay. So we lose basically excited states.
So they look like excited states on a short time scale, but over the long run, they will
tilt towards.
Yeah. So I added a small part or other questions since this ends the math part, so to say. Yeah.
Sometimes people like to add classical driving fields to these types of theories. Would this break anything?
No. No. I mean, of course, it cannot be super. I mean, there's sometimes problems if you switch it on from 0 to some value with these discontinuous jumps. There might be problems, but everything that you ramp up smoothly and things like that, there shouldn't be a problem. Yeah, no.
I mean, there are different math methods to prove things, but then they would need probably a different method like this Yajima.
Yeah. And the problem with such jumps is that usually you introduce infinite energy.
Yeah, we have infinite energies. You still have solutions,
but where should infinite energy come from? So
you can define solutions, but they physically don't make sense.
Okay, so this small epistemological part, I just added it here because it seemed to fit a little bit to this more foundational part of the lectures. And I wanted to make sense of this term ab initio, and when we talk about models and theories, just to tell you my perspective of what it could mean. So in physics, we have some different epistemological levels. I mean, for everybody, it's somehow clear what this means, but everybody might have a little bit of a different understanding what it means. And it goes from more theoretical to more applied, I would say. So theory, models, computations, simulations, experiments, right? But we clearly need all those levels to make sense of, or to do physics. And I will first go into the distinction of model versus theory, where I don't tell you a well-accepted theory, but that's just my point of view. So I would say a theory has a broad scope and is more general, while a model applies to very specific situations, physical situations. And a theory should or is thus applicable to a wide range of different effects, while a model wants, and this is the idea behind the model, it wants to relate to only one or only a few special interesting phenomena or effects. And usually you would say a theory uses only a few parameters, ideally only natural constants. I mean, that are the parameters of our foundational theories, right? While a model can contain several phenomenological parameters, and sometimes you don't even care where they come from. And the structure of a theory rests on fundamental principles, often, of course, basic symmetries, some ontological commitment. This, like, what are your basic building blocks of the theory, like electrons and fields, and that's how I use to describe them. While a model can be much more ad hoc, and then leads to quasi-particles where we don't even have a clear understanding maybe what they are, but they are incredibly useful on the other side. And now it gets more positive for the model on the model side, because now it looks like, yeah, okay, theory is better, but no. Because a theory might be complex and in principle totally unsolvable for interesting examples, very difficult to implement numerically. Think about our Fock space. How do you want to implement that? You need to put cutoffs and discretization all over the place. So while a model should always allow for a solution strategy, I think a model that doesn't allow for a solution strategy is not an interesting model, right? And through its solvability, a model can ideally be brought in direct contact to experimental results. And that is, of course, extremely important for physics, while a theory will have more the status of a structural and cognitive toolkit used for model building. So that's why I put the model in between theory and the experiment. So then I would add, like, if a model depends on a certain theory, interestingly, there could be models that are outside of theories. I mean, you just write it down, it makes mathematical sense, and then you say, the number I can read off my device. But that is not ab initio theory. So that's not linked to ab initio theory, and we'll come to this. If a model depends on a certain theory, there must be a well-defined chain of logical operations, like simplifications, reductions, aggregations, coarse graining, parameter limits, that lead from this theory to the model. So you have to explain somehow how you get from the, for example, Pauli-Fierz Hamiltonian to a Hubbard model. And sometimes not easy to describe this, this chain of operations. And there's this very nice quote that science builds models in order to save the phenomena. So I have this physical phenomena. I want some equation there that gives me numbers that describe this phenomena. So we built the according models to save the phenomena and to get what we think are explanations for physical phenomena. And applied to non-relativistic QED, I already told you that, like Pauli-Fierz quantum field theory, but then there are many models that relate somehow to this or even the fully relativistic field theory, which would be the uppest level. But here we always start from Pauli-Fierz quantum field theory. And the models would be something like the Rabi model or the quantum Rabi model, the James-Cummings model, the Davis-Cummings model, the Dickey models, the Friedrich-Smee models, the Hubbard model, and so forth. Hubbard model maybe not because there's no field. Yeah. So then what is ab initio theory? To my understanding, of course, ab initio, I will tell you nothing new, means from the beginning, from first principles. And what are the first principles? So we always, and that you will see, we always start with this basic setting of a Hilbert space of particles and field modes. And we write down the Pauli-Fierz Hamiltonian of Pauli-Fierz quantum field theory on an infinite dimensional Hilbert space. And I hope I could show you today why this is important. This is the physical setting. And that means the theory works by solving partial differential equations for given boundary conditions, and then practically using some form of discretization. Like this, they almost only rely on fundamental constants of nature. There was not many parameters involved in the Hamiltonian, right? Interestingly, I added this form factor and I didn't tell you how to choose it. So there are certain more phenomenological parameters here or more practical parts that you need to consider. But then, in order to make sense of this, one should always check if it's possible to make some infinite basis set limit. So if I make the discretization of space finer and finer, does it converge, or do the solutions and the energy or something blow up to infinity? So because if it's ab initio, I think behind that there should be still the Pauli-Fierz theory on this infinite dimensional Hilbert space. I cannot simulate the full Hilbert space, but I can ask the question, if I go to a finer and finer grid, for example, do I get better and better answers? And that is a very important thing to do in order to make sense of such a theory. What are the benefits? So, I mean, of course, this is a huge effort to do these things. So are there benefits? And I would say, yes, absolutely. So what they can do, what ab initio theory can do for you is it can explain something. So if I derive models from it, they are in a well-defined relation. There's this chain of operation that brings you from the theory to the model. So they are in relation with the established, understood. I put it under quotation mark because you have to decide for yourself if you understand the theory. It helps to discover something because it can be the starting point for new models and for systematically developing new ones or enhancing established ones. And you're not in this free-floating space of models where you can just invent a new model and you have to come up with good ideas, like out of nowhere with good ideas, or of course you have educated guesses, but it's very clear you want to relate it to this established theory that is embedded in this setting of QED, very traditional physical field. Yeah, and the challenge is, of course, by this, and this is very important, I think, you're able to scrutinize and eventually falsify the big and well-established background theory. Because it's not that we have to believe that QED is the last wisdom of physics forever, okay? I mean, it has been almost 100 years, maybe, but this will not remain like this. But if you only always work with free-floating models, you will never be able to relate this back to the big theories behind that. So only by staying in close touch to the theory, you will also be able to say, we need to extend this theory. We need to change it this or that way. And I think that's extremely important for the future because hopefully we will develop our basic theories of physics as well over time. Okay, that brings me to the end. So here's the essentials of our both lectures, Ruki and mine. So we showed you this Pauli-Fierz setting where electrons and effective nuclei ions are non-relativistic particles and photons are treated relativistic in the Pauli-Fierz Hamiltonian. The inclusion of the photon continuum implies bare particle masses, this renormalization procedure, and finite lifetimes of excited states that I've shown you in the second part. Changing the gauge, this was the length gauge example of Ruki, implies that observables are represented differently. What has been before matter and light can be mixed differently. So in every representation of your theory, this changes what you call matter and what you call light. And in the end, it's a theory of both. It's a light matter theory. So that you should remember, and that's all the thing, polaritonic chemistry, you have this solution of light and matter. I always think of particles in some fluid, but you cannot take them apart totally. A separable Hilbert space can be set up for matter and photons on which this Hamiltonian acts. We need this introduction of a form factor to make it mathematically well defined and to be able to apply this Cato-Rellich theorem to show that it's actually a self-adjoint operator bounded below. But then we have a ground state. We have one ground state. Okay, that could be degeneracy, and there is degeneracy many times from just spin and things like that. But above this ground state, there could be a gap if I have an infrared cutoff. If I have no infrared cutoff, immediately the continuum starts, and then that's it. There's no excited states. There's just like excited states with finite lifetimes inside of the continuum. So that's the spectrum of this Hamiltonian, and that one can show rigorously. Typical observables, and that's not limited to our theory here. Typical observables in quantum mechanics are unbounded operators. Thus, you need to specify their domain. Their domains could be highly non-trivial. You need to include boundary conditions to describe those domains. Yeah, and especially this is important if you now combine different sectors, these things have to fit. Else, it could be that you put infinite energy from the one sector to the other, something like that. Will not have your usual conservation properties, and you could destroy your theory potentially. Yeah, and about the models in ab initio theory, we try that our models or our discretized settings, our implementations stay close to the Pauli-Fierz quantum field theory. And this should yield a clear strategy of how models can be developed and refined for all kinds of combined light matter phenomena. And from this day on, starting this afternoon, you will see many examples how this is done. I think that's it. Thank you very much. There's still one or two questions.
One of your recaps just now, you said that the lifetime of the excited states comes from the photon continuum.
Yes.
How does that work again?
Okay. I mean, if you have an excited state, a real excited state, right? And if you put your vector in this excited state and you apply the Hamiltonian, I mean, it's an excited state. So you apply the Hamiltonian, it stays the same state, right? So if you're in an excited state, you will forever stay in this state with unitary evolution. That's infinite lifetime, right? But now in a continuum, this notion is only approximate. So it's still kind of true, but it's only approximate. So as you apply your unitary evolution, your state will stay almost the same. Slowly, it will go away. And that's the finite lifetime.
By the emission of a photon. So instead of ionizing, you ionize a photon.
Now comes the physical explanation. So you are in excited state, but there's a mode continuum here. So the mode continuum is open for all kinds of emissions. So since you're in excited state, of course, over time, you will emit photons. The photons will fly away to infinity. You go down in the matter system goes down in energy. the matter system only. The whole system keeps the same energy, of course. And that is, so said differently, that's an important idea in our community actually, but it's a very basic idea. As you, over time, you start in any state you like in your Hilbert space, over time you will go to the ground state for the matter system. Because eventually energy will disperse to the photon field, will fly away, and you slowly propagate down to the ground state. Mm-hmm. That's the physical viewpoint. Mm-hmm.
This notion of temperature or zero temperature?
In what I just said, no. I mean,
but there's a very deep connection to temperature, which merits its own lecture again, because the way how the photon field is constructed, the way how the proofs are done, can actually show that you can map this to a stochastic differential equation that leads a Brownian motion. So due to the interaction with the photon field, you acquire always, you never reach zero temperature. And actually all the statistical physics, so how you introduce temperature, and that's really, really wonderful. In quantum mechanics, you put it ad hoc. Here it's already there. It's a black body radiation. So you get temperature and all the statistics and all the statistics and all the stochastics from the start.
Okay. So I should have said yes because you said implicit.
So if I don't have proper excited states, I build like a Boltzmann distributed thermal state from this if I only have scattering states. So you said temperature is there, but how does it look?
You need an extensive volume.
And it's different, yeah. You put your whole system into, I mean, I was talking always about the continuum case when I was describing that. I should have said that maybe. But the same you can put everything in a box, and then the continuum goes away, and then you have clearly defined excited states. And that's, you need this for thermodynamics. I mean, classical thermodynamics always has a big V at one point, right? And it's not infinity, usually.